directions. The amount of power that is leaving the transmitter is a fixed amount, but as the wave travels out, the surface, the wave front, has a larger area as the distance gets greater. And that's to show that on the next slide, which is the relationship between the surface area and the distance from the transmitter or the transmitting antenna follows basically this spherical area relationship, which is 4 pi r squared. So the area of a sphere is 4 pi r squared, where r is the radius and the center. So as that wave moves out, the area increases by the square of the radius. So there are a couple of examples here where if we had, say, 1 watt at 1 meter from the transmitting antenna, the area of the sphere at 1 meter would be 12.6 meters squared, and the power density would be 80 milliwatts per square meter. So if we double the distance, so about 2 meters, the area is now 4 times the area. So that same 1 watt is now over 4 times the area, and that gives us a power density of 20 milliwatts per square meter. So the power is reduced by a factor of 4 as the distance is doubled. Okay, so that's the way we lose power, which is a significant loss. As the further we get away, we're not just increasing or decreasing the power density by linearly by distance, but by the square of the distance. What else can I say about this? So I guess the conclusion of that is when we get long distances, we get very weak signals. So we're talking about things like micro or nano watts being received, really low power. And we measure that power because these are very large numbers, or actually very small numbers. We use that dB measure, which is the logarithmic method of measuring power. So we talk about dBm as a power measure. So the idea of dBm is we measure power relative to 1 milliwatt. So 0 dBm would be 1 milliwatt. So we might have a signal at a receiver which is, say, minus 100 dBm, a fairly weak signal, and that would be basically 10 zeros, 1 milliwatts. So in terms of voltage, it would be of the order of microvolts. It would be really small. And our receiver has to be able to detect those really small signals, amplify them, and make sense of the information that comes out. Okay, so we've seen that one. So again, this is not on the exam, but I thought this would help understand that power, what we call the link budget, of getting from a transmitted amount of power to the receiver. And this is what an engineer might do when he's designing a, say, cell system, like a phone cell tower, to determine that he has enough signal for the phones at the receiver. And because we're using these things called decibels, this logarithmic measurement, instead of having to multiply all these out, we just add them. So every time we have a gain, like an antenna that has maybe a 10 dB gain, we add 10 dB. And when we have a loss, like, or we've got losses like the propagation loss, or we might have losses in the feed line, the coax, we subtract those. So basically what this link budget says is the power at the receiver is equal to the power of the transmitter plus the gain of the transmitter, which could be the antenna gain, minus the losses of the transmitter, which could be the feed line losses, minus the free space path loss, which is that square of the radius. What else we've got there? Plus the gain at the receiver. So we've got a high gain receive antenna. We make a few dB gain there, minus the loss at the receiver. And then the free space loss is this factor here, which is the R squared, or dependent on the R squared. So again, this is just so you can understand how all these pieces fit together as we get from a transmitter to a receiver, and you don't need to worry about this really down. This is an example of the power that we would receive here from the repeater on Mount Seymour, which is called VE7RBT. So it has a transmit power of 40 watts. And again, we're going to work in dB, so we convert that down to dBm. So that 40 watts represents 46 dBm, which is 46 dB above 1 milliwatt. And then we look at all of these factors. So we've got the gain of the transmitter, which is the antenna gain, and they use 4-phase dipoles, which has 10 dB gain, giving what we would describe as 400 watts ERP. So it's equivalent to 400 watts coming out of the antenna, because all of that power is focused, pointing towards Vancouver, I guess. So that 10 dB is 10 times the 40 watts, using 400 watts effective radiated power. Then we go down transmitter losses. So we've got a feed line in the transmitter, and that is 150 feet of feed line, and we get a loss of 1.2 dB on that feed line. There's also a duplexer. Remember when we talked about transmitters, we use the same antenna for transmit and receive, and we have to split out or isolate the transmit path from the receive path. That piece of equipment is called a duplexer, and it has a loss, which is 1.5 dB. Then we've got the free space loss, and that really is the biggest loss. So that wavefront traveling out through space between Mount Seymour, which is about 25 kilometers from here, to here, we lose 104 dB on that 25 millimeters. Finally, we get the signal arrives here, and I'm assuming we've got a mobile sitting in the car park, and we've got a 5/8 mobile whip on, and it has a gain of 5 dBi. Notice I'm referencing the isotropic. So it's not 5 dB. It's not 5 dB over a dipole. It's 5 dB. It's actually 3 dB over a dipole, but we've also got 2 dB between a dipole and an isotropic radiator. So 5 dB. Same on the transmitter antenna. Okay, so we've got the signals now being received, and it's going into receiver losses. So we've got feed line on the receiver. That's another dB of loss. And so now what we need to know is what's the receive now. So we basically take 46, add 10, subtract 1, subtract 1.5, subtract 104, add 5, and subtract 1. And that gives us a receive power of minus 40 dBm, which is 32 nanowatts, if we convert it to just to power. Or given a 50 ohm radio input, we measure 1.4 millivolts at that antenna receive point, which is actually quite a lot of power. That's well over SNRE. Now, there are some assumptions here in that we've got perfect line of sight. That free space path loss assumes there's nothing between us and Seymour. That is, we can actually see the transmitter. If there's anything in the way, there's going to be, because radio works like optics, if we're in a shadow, we're going to be hidden behind that shadow, and if there's a mountain or any other effect, it's going to be different. So this is, if you like, a rule of thumb on giving us a rough idea of what the power might be when people actually go and design these cell sites. They run more complicated models to determine what the received power is. Again, you don't need to know this for the exam. It's just so you can understand how all these pieces fit together to give us the signal at the receiver from the transmitter. Also, just to give you an idea of what these levels mean, we talked last time about these S units, S1 through S9, and then we've got plus 10, 20, 30 dB. So we measure dB over S9. And these are the power levels in basically reference to milliwatts. So what do we have here? We have minus 45 dBm. So minus 45 dBm will be down here. We've got a signal around S9 plus, it's not quite 30 dB, but it's close. So this is the power level and the voltage across a 50 ohm input. I think Dave said last time, each of these S points represents 6 dB. If you look at any of these, 85 plus 6 is 91, plus 6 is 27. So that's a 6 dB difference. You remember 3 dB is double the power, so 6 dB is 4 times the power. And you should see that as we go here. So 8, 22, times 4 is 8. 8 2 times 4 is 8. 8, 1632 will be 3.2, and so on. So each S point represents 4 times the power, and the relationship between voltage and power means that this is double the voltage. So each S point represents double the voltage of the receiver. And once we get beyond S9, then we measure dB over S9. So the difference between 73 and 63 is 10. The difference is 10, which is 10 dB. So it's S9 plus 10 dB. Okay, so we understand how we get some signal to the receiver. Okay, a bit more of a refresh on radio waves. So I've shown you this before. Electromagnetic waves are a combination of electrical and magnetic fields. So the electric field is in one direction, and the magnetic field is in the other direction. So if you've got a vertical antenna, as we drive the antenna with a feed line, we develop a voltage across the antenna. The voltage becomes is a peak at the end of the antenna, and that develops an electric field. And the way electromagnetism works, a changing electric field induces a magnetic field. You get that with coils when you apply when you have a moving wire, it creates a magnetic field. In this case, the wire isn't moving; it's the electrical voltage that's changing in the wire. That induces a magnetic field, and the magnetic field in turn produces an electric field, and that's how it propagates this sort of interplay between the magnetic and electric field. Very similar to the slinky over here. There is nothing physically moving in the slinky. As I shake the slinky, you get a wave traveling along the end, back again, and that is, the metal is not moving, it's just the energy that's traveling down the wave by coupling between the different pieces of the material. So